In this problem, we're determining the mass and spring constant for a simple harmonic oscillator based on the phase space diagram that's given to us and the total energy in the harmonic oscillator, which is given to us as 10 joules. So what we want to do is identify the moments in the motion of this harmonic oscillator where all the energy is kinetic and where all the energy is potential. So in our phase space plot, just a quick reminder, that's a plot of velocity versus position. I can see my moments where the speed is maximum, and this happens right here at the top of the ellipse and here at the bottom of the ellipse. At both of those locations, the speed is 4 meters per second. And we also see that the value of position, the value of the x variable, is 0 at those 2 points, so there's no potential energy in the harmonic oscillator. So recall that kinetic energy is 1/2 mv squared, and at these special moments in the phase space trajectory of the harmonic oscillator, all the energy is kinetic. So I'm going to call this E for the total energy in the harmonic oscillator is equal to 1/2 times the mass of this thing times the max speed squared. This means we can quickly solve for the mass. And that's 2 times the total energy in the harmonic oscillator divided by the maximum speed squared, which we got off the phase space diagram. So plugging in our numbers, we have 2 times the total energy, which was 10 joules. We have a maximum speed of 4 meters per second, and we need to square that. And we arrive at a mass of 1.25 kilograms. Now to get the spring constant of this oscillator, we're going to look at the 2 points on the phase space trajectory where the kinetic energy is 0 and all the energy is potential instead. And notice at those 2 points on the left and right sides of the ellipse, the speed is 0, guaranteeing that all the energy is potential energy. And our x position is either plus 5 meters or minus 5 meters, and it doesn't matter which point we use because our potential energy, I'm going to call it U here, is going to be 1/2 kx squared. So we're squaring that variable. So at one of these special points, the total energy in the oscillator is equal to the potential energy because the speed is 0. And I'm going to go ahead and call the x value there A because it's the amplitude of the oscillations. It's the maximum displacement from equilibrium for the harmonic oscillator. So we do a similar thing. We just solve for k. That's going to be 2e over a squared. And I plug in the numbers. We were told there's 10 joules of total energy, so 2 times 10 over the amplitude squared. That was 5 meters all squared. And I arrive at a spring constant of 0.8 newtons per meter. And we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.